So what we're looking at here is a half of a unit cell of one of these nanolattices that we make. Notice how here each of the individual beams is made out of self-similar elements within each beam, very much like a fractal may look. Now this particular sample is made out, it's a composite, so the inside of the beams are filled with polymer and it's coated with a ceramic, brittle ceramic material, very thin amount of that. So it's effectively a core and shell type of a structure. Now the ceramics are usually brittle materials and the polymers are definitely deformable. So what we would expect for this structure to do is to collapse brittly and to have a catastrophic collapse because it has a brittle component to it. So we have a special instrument that allows us to watch what we're doing. These are very small structures, as you can see, and bam. Hopefully you saw, you didn't miss that, because if you blink, you miss that, that this whole structure collapsed. Now, what we're going to look at is a very similar structure, but this time each individual beam, and I mean the large scale beam as well as a small scale beam, is hollow. And so we effectively took out the polymer that was there in the first sample that you just saw and made the whole structure be hollow. So you can imagine that the relative density of these structures is greater than 99%, so it's mostly air. So when we compress something like this, we would very much expect it to break, to shatter, just like the one before did, because its outer shell is still a brittle ceramic. So this entire structure that we're about to compress is, let's just remind ourselves, it's a hollow brittle ceramic, and we're going to compress it. Again, we're doing this in our in-situ custom-made microscope so that we can see what we're doing. And you can see at first we have a small collapse of the sharp top, which is what we would expect. And now you can see that we're really collapsing the whole structure. And it's almost painful to watch that we're bringing this guy down to its knees. And surely you would expect it to break at any moment now, right? You can see that everything would snap. But instead, what it did was it totally recovered. And so what you observed there was really surprising and unexpected, because brittle materials shouldn't be recovering after deformation. And this, not only did it not catastrophically fail, but it returned back to its original shape. So let's see what we can do in addition to this. What we can do is we can add more and more hierarchy to it. So let's look at the third video here. You can see that now, in addition to each beam being made out of the self-similar elements, now each one of those elements also serves as a building block for the next layer of hierarchy. So this is a third order hierarchical half cell, and you can see that each large beam is comprised of the smaller elements, and then each one of those smaller elements is also comprised of the octahedron unit cells. So what we effectively did is we built the hierarchy. Instead of a second order, which is what you saw before, we're now getting a third order. So let's see what happens here. And we're going to now compress this structure, not only once, but over multiple cycles. This is also hollow, so based on what we saw in our previous movie, we would expect the structure to recover, although it's still very, very surprising. And you see it did it. So even though it looks hugely distorted at the point of maximum compression, it's still able to recover, and not only after a single cycle, but even after the second and third and fourth. And so what we're showing you here, both in terms of the video and in terms of the data, is that there's a hysteresis in the data, so we're absorbing energy each time this happens. And so every time we're able to recover some of this energy, and the sample doesn't appear to be globally deforming, and certainly not in any catastrophic way.